Hello, I'm Stefan Mabry, a PhD student at the University of North Dakota. Today I'll be talking about a method to improve constraint handling in genetic programming. Specifically, we'll be using a symbolic regression as the genetic framework. So we're going to walk through the standard process, and we'll talk at length about the problem we're solving, and then how this contribution works, and then we'll talk about the experimental setup, results of the experiment, and then finally we'll discuss the impact of our results. So at a high level, the work's focused on symbolic regression, where the goal is to kind of recover the equation, a hidden equation, directly from the data itself. So we use genetic programming to do this, which evolves the candidate solutions as the expression trees are made up of mathematical operators. The issue is that many of these operators come with constraints. So like logarithms require positive inputs, square roots, they break on negatives, and then division by zero is a real problem. So genetic programming doesn't account for those constraints during generation, so it frequently will produce invalid expressions. Those invalid candidates still go through the search process, which ends up wasting computation and it disrupts convergence. A quick note here, we chose symbolic regression because it naturally exposes this problem that we're trying to solve. And the search space is built from mathematical operators like log, square root, division, which all have domain constraints. So that makes invalid expressions very common during the evolution. And at the same time, the problem's still controlled. We know the ground truth function itself, and then we can measure the exact error from that. And then we can isolate the effective constraint handling without other variables getting in the way. So it gives us a clean way to study how constraint handling impacts the search process, especially as those constraints start to interact with more complex expressions. So this is where the problem actually shows up in practice. Genetic programming generates candidate expressions randomly through mutation and crossover without considering whether those expressions are valid. And then because of that, you frequently get invalid expressions. So things like taking the log of a negative number, square roots of negatives, divisions near zero. And so the key issue here is that these things are not wrong, but because you can filter them out later, but they still take up time in the search process. They're getting generated, evaluated, and then discarded later on in the process. And so that wastes a lot of effort of the CPU, and then it makes the search less stable, and then especially around expressions that are more complex and where these violations can happen more often. So why does this matter? So first, some expressions simply can't be evaluated at all. If you take the log of a negative number or divide by something near zero, the result becomes undefined. Second, this starts to distort the selection process itself. Invalid candidates don't behave like normal solutions, so they interfere with how the algorithm decides to keep and what to discard. And then third, and probably most importantly, it wastes computation. So the algorithm still spends time evaluating or generating and then attempting to evaluate these expressions, even though they never contribute to a solution. The search process is effectively spending part of that time exploring regions that never produce valid results. So this isn't a new problem. How did people handle this before what I've done here? So broadly, most approaches are reactive. So constraints are handled after the candidates are generated. Most common pattern is late stage enforcement. You generate candidates, evaluate them, and then penalize or discard the invalid ones. But by that point, you've already spent compute on something that's unusable. So there's also like local feasibility checks that you can do. So some of these try to catch issues earlier, but those checks are usually very isolated, and they don't consider how the full expression behaves across the domain. And then there are structural approaches like grammar constraints. So these help prevent syntactically invalid expressions, but they don't guarantee that the expression actually works when evaluated. So, across all of these, the pattern is that constraints are handled after the fact and then only partially enforced. And that leaves a gap for how feasibility is managed during the search itself. So what are we going to do about that? So instead of handling those constraints after the candidates are generated, like far down the process, we'll just move that check earlier into the generation process itself. So when a new candidate expression is created through mutation and crossover, we don't jump into evaluation for fitness. What we're going to do first is check for validity. And so if it violates the domain constraints itself, we can just immediately reject it and then generate a new one. And so that it never enters the population. And then, of course, your population, you just replenish it with valid, like newly mutated and then more likely to be valid expressions. So to do this efficiently, we have this thing called a constraint grid, and it's a lightweight version of this. And so what it does is it's just a sampled set of inputs of the domain, and then we evaluate the expression on those points and then check for features like invalid logarithms or division instability. And then we're not trying to, change operators or restrict that search space artificially. We're just trying to generate, trying to ensure that what's generated is usable before it participates in the evolutionary process itself. So how does it work? So stage 1's unchanged. We still generate candidate expressions using mutations and crossover. Stage 2 is where things differ. So this is where I've inserted the constraint grid. So instead of immediately evaluating fitness, we're going to run that lightweight check using the constraint grid I just talked about. And then this is like that sampled inputs of the domain. And then stage 3, we're going to determine feasibility. So if the expression produces an invalid values, like the negative input of a log, then we're going to reject it and then generate your new candidate. And then that loop continues until we get valid expressions. And then we hit, we hit this retry limit. So you'll see in a minute that I put an artificial barrier so that we don't generate candidates infinitely, in the unlikely case that every candidate we generate is invalid. So after that, in stage 4, then we'll do that full fitness evaluation and then allow the candidate to enter the population. And then the real challenge here is inserting the feasibility filter before the evaluation. So everything else in genetic programming pipeline is exactly the same. So this slide shows the full experimental setup. Don't read through everything here. I'll walk you through the pieces and the details here. I'll walk you through everything so that you don't have to read everything, but the details are here if you want to reproduce what I've done. So on the left here is the genetic programming configuration. It's all pretty standard: the population size, mutation, crossover, tree depth. So those are held constant across both testing methods so that we're isolating just one variable, which is that constraint handling component, just the use of it or the not use of it. The key addition being that constraint grid, so that's the 250 points is listed at the bottom here. So that's a universal sampling of the input domain. So instead of checking the feasibility of the single input, we're going to approximate how that candidate behaves across the entire domain. And then when a new expression is generated, we evaluate those on those 250 points. So if it produces that invalid value anywhere, like a negative input to the log, then we can just reject it immediately. And then on the right here is the benchmark functions themselves that I use for this experiment. They're designed to increase constraint complexity. So the first one is pretty simple. It just introduces, so the first one is the square root. And so the square root of x has, obviously negative numbers being the invalid configuration there. And then the next one is the log values. And so that's the, again, you don't want to have negative numbers for x. And then the third one here is combining the multiple constraints into a single expression. In fact, all three of them that we've discussed so far in this presentation. And that's the one that actually produced like obvious results. Like all of them produced good results in this experiment, which we'll talk about in a second. But the one that produced the most like obvious one was the mixed result, and we'll talk about why that's important in a minute. So at the bottom here, in the section here, the metrics that I used. So the root mean squared error measures accuracy, and then invalid rate. I included invalid rate because I wanted to see like how much of the population was invalid in the benchmark test. You'll see in a second where that it goes to 0 when we kick out invalid solutions, which is not really a result, right? If you kick out all the invalid solutions before you measure if they're invalid or not, then you're going to be at 0, and we get rid of the vast majority of them. And then the third one here is combining multiple. The last one here is evaluation of threshold. So then that one's a measure of how efficiently that the method itself converges on a solution. So everything here is held constant except for when the constraints are enforced, and the constraint grid is the thing that enables that earlier filtering. So the results. This table summarizes the results across all three benchmarks. I'll focus on the patterns, not the individual numbers. So the first thing to notice here is that the invalid rate in the baseline method, around 8 to 12% of the candidates were infeasible. And then obviously for the mixed solution, well, I guess the square root is actually produced more, but the mixed solution is actually the one that the solution never evaluated fully. So in the benchmark case, in the domain that I gave it, or the range that, like the number of repetitions that I gave it. So anyway, invalid rate, 8 to 12% of the generated candidates are infeasible. With the propagation guided approach, that drops to 0 because we're kicking them all out. So 0 invalid candidates is that direct effect of the filtering before they enter the population. On simpler problems like the square root and the log, both methods achieve perfect accuracy, which is expected since they're simple expressions. So the root mean squared error actually goes to 0 in both cases because there's no meaningful difference between the final solution and the test. So that it perfectly matches the data. It's likely that, like in this case, it's likely that the genetic algorithm figured out the exact solution itself, which is not hard. It's a very simple expression. The big difference one being the mixed one, that it never figured it out fully, so it never got to a threshold evaluation. So in efficiency, log 1 on the propagation guided method, it reaches the target error with fewer evaluations. You can see that on the right here. So evaluations 1750 versus 1650. So it got there faster using our method here. And then the most interesting case is the mixed one here, where by combining those multiple constraints, the baseline starts to struggle. So it never reaches that error threshold within the allotted generations. And you can see that it's missing a value for the evaluations to threshold. So in propagation guided methods, it does reach that threshold, and then also it gets a lower error rate, right? You're at 0.08 versus 0.2. So as the constraint complexity increases, filtering infeasible candidates earlier leads to more stable and effective search behaviors. The trade-off is that propagation guided methods require more total evaluations in some cases, and but those evaluations are spent on valid candidates rather than wasted infeasible ones. And then overall, the benefit in this, you're not getting as much benefit in simple cases, but because we're keeping the search from breaking down as constraints start to interact, then we'll actually get to the right answer faster. So this is that mixed convergence behavior for mixed one benchmark, comparing the two, like the benchmark versus the propagation guided. So the blue line is your base genetic programming, and the orange line is the propagation guided approach. The shaded regions show the variance across the runs. So early on, both methods improve at a similar rate, but the propagation guided method starts to pull ahead fairly quickly. The key difference here is the stability. The baseline improves more slowly and tends to plateau, while the propagation guided method continues making constant progress. So at the end of the run, the gap is pretty clear, right? The propagation guided method reaches a lower error and it does it more reliably across runs, which reflects, what this reflects is that less wasted effort. And then the baseline is repeatedly generating and evaluating infeasible expressions, which disrupts the search. Once those are filtered out, the search stays focused on the valid regions only, and then you get more consistent improvement over time. So the pros and cons of the approach. So on the cost side of using the approach, every candidate now has to be checked against the constraint grid. It's a lightweight check, so it's not that big of a deal. And then, of course, in cases where there are no constraints, that check would be ignored. So you could add this without having constraints, and that would be also fine. So that added check against constraint grid adds computation. And then in some cases, we'll have to regenerate the candidate multiple times before we get to a valid one. There's also approximation. So the grid itself is just a sampled view over the domain. We're not guaranteeing global validity. We're just doing it over the domain period. But here the gains are more meaningful. We completely eliminate invalid candidates from the population, and then that leads to that more stable convergence and the better performance, especially as those constraints become more complex. So with the trade-off, we'll spend a small amount of extra computation up front to avoid wasting much larger amounts of effort later in the search. So there are three interrelated takeaways from this work. So the first one is the constraint handling itself is more effective when it happens earlier. Moving feasibility checks before evaluation changes how the search behaves. Second, invalid candidates are a real problem. They're not just failing, they're wasting compute, and they're introducing noise into the selection process. And third, this is a fairly simple change itself. We're just modifying the timing of error checks, and then obviously the way we're doing the check is slightly different. But we're improving stability and convergence and performance for those constrained problems just by moving that check a bit earlier. So these are the citations that I used for this whole project as a whole. So you can check these out if you'd like to. They're some really good papers. And then if you want to ask questions, this is normally the Q&A process, but obviously we're virtual. So feel free to reach out to me in Madison, or you can come to my LinkedIn page and send me a message there, or you can email me at my university email address. Thanks for checking this out. Have a great day.